The next example I want to do, you see on the board, actually is both type 1 and type 2. It's obviously type 1 because it's got an infinite interval. We've got the infinity at the top, but you can also see that it's got two things here in the bottom. There's an x and then the square root of x squared minus 4. So in our interval, of course, that doesn't make any, the x doesn't matter, x equals 0, but we can't have x being 2, obviously, and that happens to be the lower limit. So we have to break this one up into two separate integrals. One integral with the 2 as the lower limit, and the other integral as the infinity is the upper limit. And then we take two limits. It doesn't matter where we break it up, and that's one of the things that I've mentioned before, but we didn't really see. We saw maybe one integral where it was broken up at 0 because it was minus infinity to infinity. Unless it's another asymptote, that's when it matters. Like you have to break it at an asymptote. But if you're just breaking it so that you only have one limit in each piece, so we look at each piece separate, at each integral separately, then it really doesn't matter. So I'm going to break it at 3 just because it's like the next whole number, but really you could break this up anywhere. So I'm going to go s to 2 from the right. I'm going to put a 3 there. And then the next one, I'm going to use t for the infinity. Okay, so now when it comes to evaluating this integral, you see that x squared minus a squared, you can immediately do this with trig substitution. However, there is an easier way. You can't do it with u substitution, but if you remember, this kind of looks sort of vaguely familiar, right? Like an x times the square root of something. In fact, the derivative of inverse secant is very similar to this. So x squared minus 1, right? So essentially the difference is here. So it's like a scaling factor. We can change this so that it looks like u times square root of u squared minus 1, and then use this. We can always do that. In fact, we sort of have been doing it with the inverse tan, but I've just been saying, okay, you can use the inverse tan on the sheet, but it's done the same way. So you should know how to do that. In this case, this doesn't show up that often that I would think it would be worth remembering it as a separate formula. You can also, the other thing you can always do, of course, is look it up on a table of integrals, like x squared minus a squared, you know, when you're doing your homework or whatever. But in the case that you don't have a table of integrals, you don't know what to do, let me just go through really quickly and show you how this works and why it turns out that way. So we have this, and what I want to do is I want to change basically this so it has this form. The only difference is the 4 here, so it's like I want to kind of pull out a 4. You can't really pull out a 4, right, because it's not multiplied. You have to be a little bit careful about it. So what I'm going to do in terms of being careful about it here, I'm just going to rewrite it. I basically want to divide this, right? I want to pull a 1/4 out, sort of. So, but what that really means, I'm going to multiply by 1 in the form of 2 over 2. Why 2? Because I'm going to pull this under the square root. The 1/2, I'm going to pull the 1/2 under the square root, and then of course it's going to be a 4 over 4, which is 1. So that's the idea here, right? So I've got 2x, and then I pull that out, and this is going to be x over 2 squared minus, well, I don't know why I wrote it that way. Okay, I'll do it so it's in 2 steps, okay? So it's like this, right? So this 2 goes underneath there, it becomes a 4, and then I can kind of collect this. This is square root of x over 2 quantity squared minus 1. Now I want to make the u substitution to make this whole thing look like that whole thing, right? So I want u to be x over 2, and then du is dx over 2 as well. So I've got the dx over 2, and I've got that in there. So let me go ahead and start substituting. Du, right, is the dx over 2. My square root just goes square root of u squared minus 1. But then I've also got this x. I have to substitute for the x. You will notice that if I look at this, x is 2u. So even though I had one of my dx, one 2 went with the dx, I still end up getting another 2 there. So in fact, it becomes 1/2 integral of du over u square root of u squared minus 1, which is then 1/2 inverse secant of u. So that gives me what I want, inverse secant of x over 2. So in fact, if you go through the one for inverse tan and any of them, more or less something similar happens, and you always get that sort of 1 over a in front of it. 1 over a inverse secant of x over a, or inverse sine of x over a, or whatever happens to be, right? So just, this is something that's not hard to do. It's just you got to track where everything is going. If you want to just remember it or look it up or whatever, because we don't usually see this inverse secant. That's not very often. Inverse tan, you know, we see that one all the time. But inverse secant, like, very rarely, right? It's kind of interesting in this case because then we'll end up with a limit of inverse secant, and then we have to figure out what that is. So it's interesting in this particular situation. So let me go ahead and then do my integral. I know now how to integrate that. It's going to be that. But now I have to worry about evaluating it and doing the limits. And let me say, if you didn't recognize the form and you went ahead and you did this with trig substitution, it works out not that hard. Right? We did one very similar. We might even have done this exact one for all I know. But what I have then is each of these integrates to inverse secant of x over 2. And so for my first, I'm evaluating from s to 3. And then my second one, I'm evaluating from 3 to t. Okay. All right. Oh, that got lost. Okay, we didn't want that. Okay, so now if I'm going to look at this, what I have is the limit as s goes to 2 from the right of inverse secant of 3/2 minus 1/2 inverse secant of s over 2. And then my next one, all right, let me maybe do it like this. Limit as t goes to infinity of 1/2 inverse secant of t over 2 minus 1/2 inverse secant of 3/2. Okay, so what in the heck with these inverse secants? All right, so this one I have to think about some more with the infinity, but here I'm going to start with this, with the 2, right? So let me just write it. Because that's not infinite. This is inverse secant of 1, okay? Well, what is inverse, because I got 2 over 2. So what is inverse secant of 1? It's inverse secant is 1 over cosine, so 1 is equal, it has to be cosine of 1, so what's the inverse cosine of 1? It's 0, right? Because cosine of 0 is 1, right? So this is actually, this part goes to 0, and you know, I can just write it here. Since cosine of 0 is 1. All right. Now my second part, though, I have to do a little bit of work. More work than that. But actually what I could do for both of these is basically look at the graph of inverse secant. And, you know, you would absolutely be like, so you don't remember what the graph of inverse secant is? Nobody does. I mean, it's not very often that you use that. So I'm going to graph it here, but definitely go ahead and look at the graph on Desmos. If you think about it, right, we can think about the graph. If I actually graph secant, right, it's going to be like that, right, and that, and that, and it's got these asymptotes. Because secant is 1 over cosine, when we're going to do the inverse, we're going to use the same domain, right, for the inverse. So the way that we use 0 to pi for cosine, we're going to use 0 to pi for secant. So that's here. This is 0, and that's here. And so I'm taking this piece of the graph, and I'm mirroring it. So what ends up happening, let's see, here's 1. And let's put this as that pi over 2 asymptote, right? So this is pi over 2. This is going to be pi. This is going to be pi over 2. It's going to be 1. This is going to be negative 1. Okay? So this is going to go like that. And this is going to go like that. So basically I've taken this section of the graph. I'm sorry, it's very small here. I don't have a lot of space. And then rotate, like switch the x and the y basically. So you end up with this. So in fact, you can do this one as well from there. If I look at where I'm putting x equals 1, clearly here on my graph y equals 0, right? So we can use that for this one as well. Now for this part, of course, we're taking our t out to infinity, t over 2 out to infinity. So if I look out to positive infinity, right? So then it would be pi over 2, right? Because my horizontal asymptote here is pi over 2. And then I have this minus 1/2 inverse secant of 3/2. And I don't know what the inverse secant of 3/2 is, but I actually don't even need to care because look, here's a positive inverse secant of 3/2 and minus the negative inverse secant of 3/2. These two cancel out. So the only thing I'm left with is this, and my answer is pi over 4. Okay, so I have a nice answer here, right? Let me just say a couple things about that. So here you see why it didn't matter whether I broke it at 3 or 5 or 10, because these guys will cancel out in the case that everything is finite, right? And then the second thing is, do go and take a look at the graph, and you can use the graph for some of these as well. So it's okay to use the graph for some functions like inverse secant, inverse tan, inverse sine. Well, we're not going to do that one. That's not very interesting for this problems. You know, there's a couple of like e to the x, e to the 1 over x, e to the x squared, whatever. If you see something like that, definitely you're allowed to use the graph as part of figuring out those infinite limits, because sometimes it's really hard to do it in any other way.